I was discussing relatives in temperature. And we did a little experiment with some of my favorite stuff, trinitrocellulose, otherwise known as flash paper. I talked about how this stuff burns at a very, very hot temperature, several hundred degrees, in fact. And it burns so fast and so bright, it looks like magic, looks like it just disappears. But really, it comes down to the chemistry of it. Watch carefully. See if you can see the change from paper molecules to ash molecules that finally burn up into just a little bit of smoke molecules. Hopefully you used your skills of observation. Hopefully you're able to check that out. Now, talking about temperature and how it's relative. Yeah, several hundred degrees when I was burning the flash paper. Us humans, our temperature is usually right around 98.6 degrees, so almost 100 degrees. And of course, we're breathing in vital oxygen that gives our blood the sustainability it needs. And then when we breathe out carbon dioxide. Scientists call carbon dioxide CO2. And again, it's because they're talking about atoms that come together to make molecules. CO2. So C, one carbon gas atom. O2, two oxygen atoms. You bring these atoms together and you'll get your carbon dioxide molecule. So when we're breathing out our carbon dioxide, it should be about a temperature of about 98.6 degrees, give or take a little bit. What I have right here is a canister of pressurized, concentrated carbon dioxide. I got a bunch of it in here. And if you feel this canister, it feels, temperature-wise, room temperature, probably about 70, 75 degrees or so. Let's say I take this pressurized canister, however, and I put it into my little mad science hand cannon, kind of like this. Again, some safety goggles. Safety first, folks. And this glove right here. Now, what should happen with the hand cannon is I'm going to pull this lever over. It's going to poke a small hole into the carbon dioxide canister. Since there's so much pressurized gas in here, this stuff is going to need to escape real fast out of the top of this thing. Keep in mind, temperature-wise, like I said, this canister, it's probably about 70, 75 degrees or so. Watch carefully, folks at home. Let's see if I can poke that hole into this CO2 canister. Let's see what happens. On 5, 4, 3, 2, 1, and blast off. All right, so we blasted the carbon dioxide out of there. And what's really crazy, I don't know if you can see that at home too well, this canister, super, super cold, super cold. That's because carbon dioxide is actually naturally a pretty cold gas. And of course, the more it's pressurized, the colder it gets. So when this released, oh man, it made this canister out here get almost frozen. But speaking of frozen carbon dioxide, folks, maybe you've seen this stuff before. Frozen carbon dioxide is way colder than our carbon dioxide, which is about 98.6 degrees. In fact, it's colder than the freezing temperature of water, which is 32 degrees. In order to freeze carbon dioxide gas, you have to get it into below zero temperatures, negative temperatures. And if you can get carbon dioxide as cold as 109 degrees below zero, you'll get this stuff. This, folks, is dry ice. You'll notice whenever Radical Rob is dealing with the dry ice, I'm never ever going to touch it with my bare skin. If you were to do that, After just a few seconds, you would get a burn called frostbite. Frostbite is happening when your skin cells are actually freezing and dying. It can be very dangerous and very deadly. If you're ever doing any dry ice experiments at home, make sure that you never have skin contact with it. Use some gloves. Use a towel. Make sure the gloves or the towel are totally dry. If they're wet, they're going to freeze, and in turn, they're going to freeze your skin too. All right, let's take a close look at some dry ice. All right, folks. Frozen carbon dioxide. Now, if you look carefully, you should be able to see a little bit of what looks like steam or fog coming off of the carbon dioxide. It's not steam or fog. Steam and fog, they come from H2O, water. This stuff, when it turns, that process is called sublimation. Sublimation is when a gas goes straight from a solid to a gas or a gas to a solid, and it skips the whole liquid phase. Now, if I want to make this stuff sublimate a little faster, we add more heat to it. If I put my 98.6 degree carbon dioxide onto this 109 degrees below zero carbon dioxide, check this out. It's going to sublimate a little bit faster and a little quicker too. Now, there's a lot of cool experiments that you can do with dry ice. One simple one is where we talk again about molecules. This metal spoon right here can be a really good conductor of things. Metal is a great conductor. It can heat up really well. It can have electricity pass through it. A lot of metals can become magnetized. If you're ever in a thunder and a lightning storm, don't be anywhere near a metal structure. Metal likes electricity, and electricity likes metal. Now, let's say I wanted to use a force of physics to heat this up. I could simply use friction. Friction occurring when objects rub against each other, just like how I'm rubbing the back of the spoon right now. What's that doing to the spoon? Well, it's heating it up. It's making the molecules of the spoon speed up and get lighter and move quicker. The molecules of the dry ice, however, are totally opposite. They're cold, they're pressurized, they're not moving very fast at all. So if I take a hot spoon and I put it onto a cold piece of dry ice, apologies in advance, folks. It's like nails on a chalkboard, and then it stopped. Why did it stop? Well, if you look carefully, the spoon is pretty much frozen from just a few seconds of contact with the dry ice. So the molecules essentially are moving at the same speed, therefore they're not making any sounds. They're not really vibrating against each other. It's kind of warm out here today, so let's say Radical Rob wanted to give his bald head a little brain freeze, y'all. Brrr! If you look, the frost on the spoon has disappeared now because of my 98.6 degree body temperature. Now that's just one thing that we can do with the dry ice. And of course, whenever I talk about the dry ice sublimating, it needing to heat up in order to sublimate, there's usually some kid, usually some boy who's like, well, Radical Rob, if you're going to heat it up, why don't you try lighting it on fire, dude? All right, fine. Watch carefully. See the flame? Dry ice onto the flame. Hey, wait a second. Let's try that again. Oh, it swallows it, essentially, which is good. Carbon dioxide is not a flammable gas. It's a gas that will put fires out. It's a gas that can be used in fire extinguishers. And it's a good thing. If carbon dioxide was flammable and you went to go blow the candles out on your birthday cake, boom, your face would blow up. And that wouldn't be very much fun for anybody. However, we can alter the dry ice a few other different ways. I got some more over here. I got some little pieces of it. I'm going to take some of these little pieces and I'm going to put it into what we call an Erlenmeyer flask. Erlenmeyer, scientist who came up with this idea of, hey, what if we put a tube on the end of the flask and we can connect hoses and we can build up pressure or release pressure and do multiple chemical reactions with it. Let's say I take a couple little pieces of this dry ice right here, like this guy, and maybe this one. Oh, kind of big. Might need to break that one. All right, bear with me while I smash some dry ice, y'all. Don't try this at home. Yeah! Okay, there we go. All right, so now we got a few little baby pieces of the dry ice going. And again, if I wanted to use a little bit of friction, I could start to move it around really fast. And just that friction alone is going to heat it up and make it start to sublimate out of the top. However, if we really want to make it sublimate like crazy, all we got to do is add some hot water to it. I'm going to carefully take my beaker. I'm going to come over here with my hot pot. Kids, when you go to college and you're living in the dorm rooms, get one of these. It'll save your life. Pasta, soups. Okay.
Ramen noodles, Radical Rob. Ramen
Absolutely,
noodles.
ramen noodles were a
college
savior.
days.
I used to chop up hot dogs and put cheese up in the ramen. Okay, so this should be some serious sublimation, y'all. Watch carefully. Beaker, because it has a beak. Into the Erlenmeyer flask, like so. And we're getting some serious sublimation going on, y'all. Now, the dry ice is still not melting. It never ever melts. It goes straight from a solid to a gas, gas to a solid, sublimation. But if you look carefully, it's bubbling up through the Erlenmeyer flask, through the hot water, in order to escape out of the top. It's sublimating at a very high rate. You might wonder what would happen if I touch it. Should be fine. Kind of nervous though. All right, I can do this. Should be fine. Ah! Actually, yeah, just kidding. It doesn't really feel like anything. It feels actually a little warmer than the air that's around us. So, a few other things that we can do with this sublimated carbon dioxide. Again, I was talking a little bit about building up pressure or releasing pressure. If I put this balloon over the top, we start to heat it up, it's going to start to inflate like this. And get bigger and bigger and bigger and bigger and bigger because the gas has to go somewhere. When it expands, it's going to fill this thing up. And then, of course, if I wanted to, I could blast this thing out, whoa, on you guys like that. But then we can do another little experiment too. So, Molecular Mike, I was noticing that while I'm over here slaving away doing experiments for everybody, you're over there munching your little grain protein bowl.
That's true.
And I'm kind of jealous about that.
Okay.
You never think to yourself, well, I wonder if my friend Radical Rob's hungry at all. Well, yeah, I kind of am hungry, Molecular Mike. You know what it tastes like? It tastes kind of like a soda. When you open a soda and it fizzes and it bubbles, that's carbon dioxide gas coming out of it.
Do it again, let me
Sodas
see.
Are carbonated beverages. But you know what else it kind of tastes like? It kind of tastes like Tastes like a big burp, because whenever you burp, you're burping up carbon dioxide too. Now, if the gas has to go somewhere, if I press this in a little bit more, what do we think might happen if we plug up this hole right here? Let's see. Oh, well, it blasted off of there. Let's say I put this thing in a little deeper, building up more pressure. Man, this thing is really wanting to escape quick. It's only going to blast a little bit. Oh, thanks. Now, we understand how that works. The sublimation, I mean. Passing through hot water in order to make potions. But let's say we want to take the whole potion thing to the next level, y'all. I have another flask here. This one's a little different. This is called a Florence Flask. If we look at the differences, it's a little bigger. This is more of a triangle, where this is spherical, circular in shape. I'm going to take the Florence Flask, and I'm going to put some dry ice into it. Crush a few more pieces up again. If you remember, dry ice is carbon dioxide in frozen form, and you have to get it at least as cold as 109 degrees below zero in order for it to freeze. There we go. There's one there, one there. Awesome. And then a little bit more of the hot water. Okay. Bring this out of the way here. Cool. Okay, so we want to make this thing sublimate really fast again, just like the Erlenmeyer flask did. Cool. Again, some serious sublimation, y'all. All right, nice. So again, the dry ice is not melting. It's going through the hot water in order for it to sublimate. But then, if we really want to turn this up a notch and turn it into a crazy bubbling potion, I could take this blue chemical over here and add some of it to this. Watch carefully. I'll get this dry ice out of the way first, just in case I don't accidentally touch it. Okay, you might not know what this blue stuff is yet.
I was just about to ask what it was. Okay,
oh
go
man,
ahead.
I think after just a couple seconds, Molecular Mike, I think you're gonna figure it out.
Okay.
It ain't blueberry Gatorade, okay? I'll tell you that much. Okay. It's starting to change. Watch this.
Whoa, I bet I know what it was.
Yeah, dude.
Yeah?
Detergent soap, man.
Wow.
Regular dishwashing detergent soap right here. What's really cool is that the detergent soap traps the carbon dioxide with its bubbles. But then, if you want, you can crush the bubbles and release the carbon dioxide. Again, this is just dry ice, hot water, and detergent soap coming together to make a crazy cool bubbling potion.
Radical Rob, can you still buy dry ice in grocery stores?
Yeah, so you do have to be 18 or older to purchase the dry ice, so maybe you can talk your parents into buying some for your kids. But where a store that typically carries dry ice, Smart and Final stores typically carry dry ice. Now, before you go on a big shopping spree, you want to call the Smart and Final store, because we've had several instances where we're going to do a big crazy mad science party and we need several blocks of dry ice, and sometimes that stuff sells out, especially like in the heat of the summer when people are going camping and they need to have their dry ice to keep their food cold. Also, a key time for dry ice is right around Halloween. A lot of people use dry ice for different experiments, different crazy, cool, sort of spooky experiments too. Sweet. Coming up on that.
And then other clever places to get dry ice. Sometimes my family from Kansas City sends me Kansas City barbecue.
Oh yeah.
And when they ship things all the way across the country that need to be frozen, they freeze them in their freezer and then put them in a disposable cooler and then fill it with dry ice. And as much as I love Kansas City barbecue,
yeah,
the first thing I do is pull out the dry ice and start doing dry ice tricks.
I like your style.
Yeah.
I like your style, Molecular Mike. That's good stuff.
Yeah.
Cool. Well, let's see if we really want to take the dry ice to the large level, then we can create the big potion with it. And essentially, if you get yourself a bigger container or a bucket, something like this, a good sized chunk of the dry ice too. Who is it? Yeah, this guy. Maybe that guy. Maybe just a few more right here. Cool. Again, we got our dry ice in our bucket, moving it around. Gonna create some friction too, making it start to sublimate out of the top a little bit. Let's say we want to take that to a much larger level. Check this out.
I like your style, Radical Rob.
Thanks, man. A cauldron. A cauldron that starts to sublimate over the top. Mwahahaha. Now, what's really weird is that most of the time when things turn into gas, they go up in the air. This is not going up. It's going down. And it's going down because carbon dioxide, it's a much heavier gas than, let's say, oxygen or air. And what's really cool around Halloween is that you can create some really spooky, like foggy, almost like cemetery or graveyard special effects. I remember growing up watching the Scooby-Doo cartoons. They'd always be cruising through some sort of spooky graveyard that would be covered in a layer of fog. All right, so you saw what happened when I blew onto the carbon dioxide frozen state by itself. Check out what happens when you blow into the big cauldron. Whoa, that's some serious sublimation, folks. It is a little bit warmer than the air that's around us. Around Halloween, a fun thing that you can do is you can create a big punch bowl. You can get some dry ice and some good, like, purified drinking water, or even some juice. If you let the dry ice sublimate completely in the punch bowl, you will have turned it into homemade soda. Then what we like to do is we like to go get like some fake eyeballs from Party City and put them in the punch bowl as well, and then drink our carbonated homemade soda full of eyeballs. Awesome. Again, just to recap some things about dry ice, it is frozen carbon dioxide. It is 109 degrees below zero in order for it to change. It never ever turns into a liquid. It goes straight from a solid to a gas or a gas to a solid, and that process is called sublimation.
Sublimation.